So in the previous sessions we discussed with classical control engineering theory, which is a transfer function based approach. Now we are entering into a different part. It is a state variable characteristics of linear systems. Linear systems only we will be taking. Linear system is the system is in linear, the output is proportional to the input. It is a linear systems. In other words, it is only varying with respect to one space coordinates. Y is equal to mx plus c, like that. The form will be a linear. And let us recall the state space approach what we have done. State space approach is one where the differential equations are converted into a algebraic equations using vector matrix notation. Then we will be solving a matrix. That approach is nothing but state space approach. So the advantage here is, since we have matrix or algebraic equations, it is easy to compute that in a computer also. We can program any control system into the computer. So MATLAB, almost it is based on the state space variables, the state variable characteristics. It is based on that only. We can fetch the transfer function in a matrix form. The computer can easily understand. So let us see how the state space variable or state variable characteristics of the systems will be represented. First I will take a spring mass system. So this is a mass m which is having a displacement x of t. Even I can consider x double dot, x dot like velocity, acceleration, etc. And a force subjected f of t. So this is a spring mass system. The spring mass system, basically here how to model this, I will take rate of change of momentum d by dt, rate of change of momentum. So rate of change of momentum d by dt of mv is equal to the applied force. Mass will be constant, d by dt of velocity will be equal to f. Since f is a variable, the f varies with respect to time, even the velocity will also varies with respect to time. After this, I want what is velocity. Velocity is given by v of t is equal to d by dt of v of t equal to 1 by f into f of t. So what is the velocity here? Velocity can be written as, I need to remove the differentiation. So I need to integrate this 1 by m integral of f of t dt. So the limits will be minus infinity to plus infinity or plus t. That is the limit we can take. Then after this, the velocity can be represented in terms of displacement. That is also possible. Instead of moving minus infinity to t, I will split the integral 1 by m integral of minus infinity to t naught f of t dt plus 1 by m integral of t naught to t f of t dt. So this term, the first term will be represented as initial condition v of t naught plus 1 by m integral of t naught to t f of t dt. So this is v of t. The vector v of t is represented in this form. Basically what we are doing here is, we are considering the initial conditions. So these initial conditions are nothing but what are the states of the system. These are nothing but state. V of t naught is the velocity at initial stage. Let us try to write the same expression for the displacement. Displacement is given by x of t. So whenever we consider velocity, velocity will be equal to x dot. X dot is nothing but dx by dt If I want displacement, I need to integrate the velocity. So directly I will write minus infinity to t v of t dt. This is the velocity. Then again I will be splitting the integral minus infinity to t naught v of t dt plus t naught to t v of t dt. So what is this? I am representing x, that is displacement. Then after writing this, what exactly is this? This is a initial condition of velocity. So it will be x of t naught plus, again continuing this, what we will write, integral of t naught to t v of t dt. So this is x of t. Then again x of t will be equal to x of t naught plus, again I will substitute the value of v of t here. What is v of t? T naught to t. What is v naught? 1 by m, v of t naught plus 1 by m integral of t naught to t f of t dt into this integration. So I am substituting the value of v of t. So substituting v of t. After getting this value, again I will split the integral. X of t will be equal to x of t naught plus integral of t naught to t v of t naught plus 1 by m integral of t naught to t, and this is t naught to t double integration f of t dt into dt. After getting this, integral of t naught to t into v naught dt can be represented as, so this and this you can represent, this you can represent as x of t. So then what we can write is x of t naught plus the integral, if you apply this t minus t naught, you will get t minus t naught, that is upper limit minus lower limit, into you are substituting it for v naught. V of t naught will become v naught plus 1 by m t naught to t, again t naught to t f of t dt. So this is the equation for displacement. Basically what we are doing is we are expressing a displacement in terms of a periodic function. So if I write like a Fourier series, x of t naught plus integration t naught to t v naught, again like that, second degree, x of t naught, x dot of t naught, x double dot of t naught, it will go like that and finally it will end. So basically we are representing a system in terms of a differential equation in Fourier series form. So this is a Fourier series form, general Fourier series. Then further this can be converted as a state variables. Here what exactly this equation will be giving is, first initial condition, then x dot, then x double dot, like that it will go. So some of the important things what we can note is, if I consider multiple input, multiple output systems, I will consider U1, U2, etc. up to UN as inputs. Also Y1, Y2 up to Yn as outputs. During the conversion of outputs to inputs, we can determine x1 dot x2 dot etc. up to xn. These are nothing but states. When we represent u1, u2, u3, we will write they are input variables, y1, y2, y3 output variables, u1, u2, x1, x2, x3 are state variables. Whenever you want to transform an input from output, you will get a different states. This is a concept of state variables. Let us see some of the important definitions. Here you have to know what is state, then state variables, then state vectors, then state space, then state trajectory, then state equation or state model. So these are important definitions or terms. Generally, this will be asked for 8 marks. You have to write the definition of these quantities. And x of t naught, these are nothing but they are all states. If I represent x of t naught, that is initial state. If I write anything with respect to time 0, then it is called as state. If I write anything after t1 to tn, after initial state, if I write x1, x2, x3, x4, x0 is a state. If I write x1, x2, x3 up to xn, it is state variables. They are nothing but state variables. If I take the vector sum of all the state variables, then it is state vectors. If I take vector sum of all state variables, it is state vector. If I take a space is having the coordinates x, y, z. If I define the states with respect to coordinates, they are nothing but state space. The space is nothing but x, y, z coordinates. Then the last one is if I take the locus of all the state space or state variables, then I will get a plot. That plot is nothing but it is a trajectory. Then a state equation or a state model, this itself is an example of a state model. So if I write a state equation, x dot will be equal to ax plus bu, this is a one form, and if I take an output equation, y is equal to cx plus du. So this is state equation and this is output equation. So two things will be there. Let us see what are the definitions. First you have to understand what is state and what is state variable. State is nothing but state of a dynamic system is defined as minimal set of variables. So minimum set of variables, they are nothing but they are state variables such that we need to determine what is the time interval such that knowledge of vector at t is equal to t naught. Generally, instead of vector, you can use variable. Knowledge of variable at t is equal to t naught together with the knowledge of inputs. So, we will be determining what is the time interval at t is equal to 0 for corresponding input for t greater than or equal to 0. completely determines at t is equal to 0, at t is equal to t naught. They are the several times. T is equal to 0, t is equal to 1. Here, t is equal to t naught. It is an initial condition. In that initial condition, what is the behavior of the system? Completely determines behavior of the system at t greater than t naught. This is nothing but a state. Example for that is initial displacement. So x of t naught. Displacement is x of t. If you calculate displacement at t is equal to t naught, it becomes x of t naught. That is nothing but a state. Then again initial velocity v of t naught. V of t at t is equal to t naught. It is an initial velocity. So here x of t. What is this x of t? X of t is the state variable. But x of t naught is a state. Like this, the differences you have to observe. Then let us see what is state variables. State variables, so state variable involve in determining the state of the system x of t. So state variable is one which determines what is the state of the system x of t. The example for that is x1 of t. That is one of the state variable. Similarly, x2 of t. Similarly, up to xn of t. They are nothing but the state variables. These variables are nothing but state variables. And y1 of t up to yn of t, they are output variables. And u1 of t up to un of t, they are input variables. Then state vector. State vector, simply we can say it is vector sum of all state variables. If you write this in vector form, it will be a, if I write x dot of t, x1, x2, x3 up to xn, I am representing the state variables in the vector form. Similarly, y of t, output variables, y1, y2 up to yn. This is an output vector. Then state space. State space is one if you represent a state vector with respect to coordinates. State vector with respect to if you represent state vector with respect to space coordinates, they are nothing but a state space. Then state trajectory. Trajectory, it is basically a locus, so it is the locus of state vector with respect to time. State vector with respect to time. Whenever if you consider a state space and state trajectory. Here we will consider time as an implicit variable to the input. So these are the important definitions you have to read. That will be asked for 8 marks, 8 to 10 marks. So state is determines that it is the state of a dynamic system is defined as minimal set of variables, which is state variables, which represents the knowledge at t is equal to t naught, x naught, v naught. They are nothing but it is the states. If I consider x1, x2, x3, they are nothing but state variables. State variables, it involves determining the states of the system x of t other than, you can write other than t greater than t naught. State vectors are nothing but it is a vector sum of all state variables. If you write state variables in terms of vectors, it is state vector. If you represent the same vector with respect to time, it is nothing but state space. Space is nothing but xyz axis. State trajectory, it is a locus. Determine what is x naught, what is the output at x naught, what is the output at x1, what is the output at x3, output at x4. Plot the locus, you will get a trajectory or a path. That is nothing but state trajectory. Here we have to consider time as an implicit variable to the input. State equations or state model. This is a state equation or state model. So we will be deriving that expression. Just you have to write what is a state equation. These two are the state equations. They are called as state model or state space model. Many names are given to that. Let us see what is the state model of a linear system. A linear system is one which depends upon only one space coordinator x. If it is a non-linear, it will depend upon several parameters. Let us see how to write a state space model for this system. Usually, initially the conditions will be in the form of a differential equation. So if I consider x dot will be equal to d by dt of some function, d by dt of x. So if I represent this d by dt, it is in differential equation form. It might be a function of x and t. If the inputs are u, it will be x and u, the function x u comma t. If it does not varies with respect to time, it is time invariant system. If it varies with respect to time, it is time variant system. So here we will consider the time invariant system where x depends upon only x and u is the input. Then here f is a differential equation function. It can be any function, sine, cos, cosine, etc. It can be any function. So this represents a functional operator. After solving this in a matrix notation, the differential equations are converted into an algebraic equations like this. So x dot is a function of u and v. Here also x dot is a function of a1x, a2x. It is a polynomial equation of x along with the inputs. Inputs are u. If I recall a system, this is multiple input, multiple output system. These are the inputs u1, u2 and y1, y2. These are the outputs and x1, x2. These are the states. So these are the inputs, outputs and these are the states. The states depends upon x as well as u. So if I write the expression, it will be up to a1n, x1n. Similarly, x2, this is a polynomial equation. Up to xn, this is a polynomial equation. If I write x dot will be represented as ax plus b into u, where x dot is a state vector. A is, they are coefficients. A can be a11, a12, a1n. So So A21, A22, like that, ANN. So it is a matrix. It is a matrix. A is a matrix. B is also a matrix. The matrix which consists of B11, B12 up to B1M, B21 up to B2M, Bn1 up to Bnm. These are square matrix where x is a vector. So if I write that x1 dot, x2 dot, x3 dot up to xn dot will be equal to, what is this A? A11, A1n, ANM, ANM into x1, x2 up to xn plus B is this B11, B12 up to B1M, Bn1 up to Bnm into U1, U2 up to Un. So this is how we write a state model for the linear system. X dot is equal to Ax plus Bu is the state model, where A and B are the matrix, X and U are the vectors. Vectors means these are the vectors. Similarly, let us see the output equation. Output is also dependent upon X as well as U, state variables as well as an input. So if I write an output equation, we will get coefficients like this, C1 to C1x, D1 to D1x, like that. So Y1, C1x up to Cn and D1 up to Dm. Like that, if I write an output equation, Y will be equal to Cx plus Du. You have to observe one thing here. State equation starts with x dot. Output equation starts with y. Nowhere we are writing u is equal to something here. Very important thing. Again, if I represent the same output equation, y is y1, y2 up to yn is equal to, C is also a matrix, C11, C12 up to C1n, C21, C2n, Cm1 up to Cmn. This is one matrix along with x1, x2 up to xn plus D is also a matrix, D11 up to D1n, Dnm up to Dnm into U1, U2 up to Un. So this is how we represent an output equation. If I take a state model or state equation, if I take this, then x dot will be equal to Ax plus Bu, it is state equation, then y is equal to Cx plus Du. So this is state equation and this is output equation. These two together called as state model. This is how we will write a state model. Let us derive an expression for transfer function of a state model. When we solve the problems, these steps you will be knowing. First, what is state equation? X dot will be equal to Ax plus Bu and another one is y is equal to Cx plus Du. These two are the state equations. If I take a Laplace transformation, apply Laplace transformation. If I apply Laplace transformation for this, x dot, x into x of s will be equal to a into x of s plus b into u of s. This is a Laplace transformation for that equation. Similarly, apply Laplace transformation for output equation. Y of s will be equal to c into x of s plus d into u of s. What is the transfer function? Transfer function for multiple input, multiple output system. So these are inputs U1, U2 up to UN, and these are output Y1, Y2 up to Yn, and X1, X2. These are the states. What is the output? Output are nothing but Y, and what is the input or U. So Y of S by U of S is the transfer function for the multiple input, multiple output system. Let us solve the same thing. I will segregate X of S into one side. So X of S minus A will be equal to B into U of S. So whenever if I write S minus A, this is a matrix, so that's why I will multiply with identity. I is identity matrix. So X of S is will be equal to Si minus A is equal to B into U of S. Then I need X of S equation in terms of Y of S. So I will be using this. If I use that, what happens? X of S, I will substitute X of S here. So Y of S minus D into U of S will be equal to C into X of S. X of S will be equal to Y of S minus D into U of S divided by C. I will substitute the value of X of S. Y of S minus D into U of S divided by C into Si minus A equal to B into U of S. So I need to take U of S on one side and Y of S on other side. Then what I will get is Y of S, C I will send here, Y of S minus D into U of S equal to, this will get B into C into U of S divided by Si minus A. So 1 by A, it is A inverse. Y of S will be equal to B C Si minus A inverse into U of S. Also I will consider this plus D into U of S. If I take U of S common, then Y of S divided by U of S will be equal to BC. What is A inverse? If I take A inverse, it is adjoint A divided by determinant A. I will write this adjoint of Si minus A divided by determinant of Si minus A plus D. So this is how we will calculate transfer function for the state model. Very important, B, C and D are the matrix, because of which this will be also a matrix. We need to calculate what is the order. B, C and D are the square matrix. So this is about the transfer function for the state model. Let us solve some of the problems to know these things.